The objective of this video is to review the Fourier series representation of periodic waveforms and relate it to phasor analysis. When we're studying electric motors, we're inherently dealing with periodic waveforms, whether that's the current linkage in the air gap of our machine or the voltage at the terminal of our machine. And so these quantities can be periodic both in spatial nature, so that current linkage is spatially distributed along the air gap of our machine, whereas our voltage waveforms are transient, they're distributed in time. And in dealing with all these quantities, it's very helpful to be able to break them down into their harmonic components, to be able to talk about the individual frequencies of this. And our tool of choice for breaking down a harmonic signal into its harmonic components is the Fourier series. And what we're going to show in this video is its equivalency. We're going to first review the Fourier series, and then we're going to show its equivalency to phasor analysis, because we're going to be wanting to talk about an individual harmonic at a time. And our choice for representing sinusoidal quantities as electrical engineers is phasor analysis. So we want to be able to take a transient or a spatial waveform, turn it into a Fourier series of its harmonic components, and then zoom in and talk about each individual component in phasor form to talk about its phase angle and magnitude. Let's start by reviewing the Fourier series. And what this expression tells us is that we can represent a waveform as a Fourier series. So capital F of theta is the Fourier series representation by being the sum of coefficients which are labeled as A and B. And these coefficients have a subscript which indicates their harmonic index. So A0 is a DC quantity. It does not vary with the angle theta. Well, in here we've got this summation that shows that we have these terms, AN and BN, that are multiplied by cosines of harmonics of theta. Harmonic means that we have integer multiples of theta. So the fundamental period is harmonic 1, n equals 1, where we go by cosine of theta and sine of theta. Whereas if n equals 2, we say that's the second harmonic, n equals 3 is the third harmonic. And these coefficients are calculated by going back to our original waveform, our source waveform, which is this lowercase f of theta, and integrating it by either the cosine of n theta or the sine of n theta. And these coefficients are calculated for specific values of n. The A coefficient, an, is calculated for n being greater than or equal to 0, while b, when n is equal to 0, is just simply 0. So in this case, it's only calculated for n being greater than or equal to 1. Let's practice doing this. Let's practice calculating the Fourier series of the current linkage of a full pitch coil. So if you go back to your notes where we introduced the current linkage of a coil, you'll notice that the current linkage for a full pitch coil can be plotted as follows. So this is a plot of the current linkage of our full pitch coil. This is also our function, little f of alpha. So we're going to calculate the Fourier coefficients. We need to integrate this little f of theta over negative pi to pi times a cosine or a sine. And in this case, our source waveform is theta of alpha, our current linkage. And so this little f of alpha becomes the source that we plug into these expressions. So now we'll directly calculate AN and BN. And A0, which is just the integral from negative pi to pi of our current linkage, has to be 0. This is by definition because the current linkage cannot have a DC component. That was required by the conservation of flux, the fact that we had no magnetic monopoles. And so for the remaining terms, we'll break up our integral into distinct regions. This region over here, where our current linkage is always negative ZQI by 2. And to keep the math a little bit simpler, to minimize the number of terms, we're going to define this quantity theta pi, which is just equal to ZQI by 2. So when you see a theta pi, it means ZQI by 2. So we'll have one interval over here. This is interval 1. We'll have a second interval in here where our current linkage is always equal to theta pi. And then we'll have a third interval out here where current linkage is again equal to negative theta pi. And we finally get this expression for a of n. And notice that we've got this sign of n times pi by 2. That means that a of n is going to be 0 for any even value of n. Okay, we've calculated a of n. Let's now calculate b sub n. And from looking at this expression and noting that sign is symmetric about alpha equals 0, we can notice that b of n is always going to be 0. And we can bring all this together to write our final expression for our Fourier series. This first term right here looks like the magnitude of a phasor. We'll call this theta n hat. And the second term right here is actually what determines the phase angle of our phasor, whether it's at 0 degrees or 180 degrees. We'll come back to that later. But we can rewrite this as saying that our current linkage ends up being the sum of individual harmonics, where each harmonic we're denoting as theta subscript n. And we can talk about individual harmonics as follows. Our fundamental harmonic is theta subscript 1, and that's simply just equal to 4 by pi times theta pi times the cosine of alpha. Our second harmonic is equal to 0 because a2 equals 0 and b2 equals 0. Our third harmonic, our fourth harmonic is 0 again. And to write each of these harmonics, I'm just evaluating this expression up here. I'm plugging in a value of n for this theta of n, this theta sub n. And that is what I get here. So when n equals 1, this expression evaluates to 4 by pi times theta pi times cosine of alpha. When n equals 3, we get a negative because the sine of 3 pi by 2 is a negative 1. And then we can get 4 by 3 pi times theta pi times the cosine of 3 alpha. In summary of this example, this is the Fourier series representation of the current linkage of our full pitch coil. Let's now talk about how we can convert a Fourier series to phasor form. And this is also known as amplitude phase form. I'm not going to prove this, but you can derive it yourself. We can convert, we can take our Fourier series expression up here, and by doing some mathematical operations, we can rewrite it as this series of cosines right here, where the magnitude of each cosine is related to our Fourier coefficients, a sub n and b sub n. And the angle of each cosine is again related back to our Fourier coefficients, b sub n and a sub n, through the arctan. And so we can take this expression and we can now write it as a series of phasors. And we get this final expression. So now we've figured out that we can construct a phasor for each harmonic. That's this Fn bar. And Fn bar has a certain magnitude and a certain angle, and that magnitude and angle are related back to our Fourier series coefficients. So what I'm telling you is that I can give you some periodic signal. You can then use the definition of the Fourier series to construct the Fourier coefficients. And you can convert from those Fourier coefficients to phasors for every single harmonic. For every single individual frequency component, you can construct the phasor. And you can relate this back to our previous video on phasor analysis to then construct a phasor diagram and talk about how you can add or subtract individual phasor components. So this is a powerful tool. It's a tool to use for analyzing the periodic waveforms that we're going to be dealing with frequently in this class. And I want to note that this, of course, is not specifically tied to spatial quantities. Right now we've written this out in terms of theta, but we can relate this to transient quantities by noting that theta can equal omega t. So, for example, we can talk about a voltage waveform which has rich harmonic content. It can be a voltage waveform that has got a DC component and then several periodic components. And we can express this as a phasor for each of those harmonics. These are these Vn phasors here. And these harmonics occur at harmonic indices n of omega. And for every harmonic, we can again sketch the phasor diagram. We can talk about the phase angle of that harmonic, the location it is in time, this Vn, and we can talk about the magnitude of it. And then we can talk about the frequency that this phasor diagram rotates at. So this closes the loop. It brings us back to phasor analysis, from Fourier analysis to phasor analysis. Let's consider another example. We'll call our first example example 1, and our new example example 2. Suppose that we want to remove the fifth harmonic of a winding's current linkage by adding a coil. We're going to consider the example winding from example 1. So in example 1 we had a single coil winding. We're going to add a new coil that is angularly displaced. It's rotated from the first coil such that it cancels the fifth harmonic. What should the angular separation be between the coils? Let's draw what this question is asking. So we've got our original coil that's aligned in the top and bottom, and we've now placed a new coil that's rotated phi c radians from the original coil. And the question is, how much should that rotation be so that we cancel the fifth harmonic of the current linkage? We're going to assume that both coils have the same number of ampere turns, and so the new coil creates the same current linkage as the first coil, but it's rotated by phi c radians. So let's write this out. Our total current linkage we'll call capital theta of t, and it's going to be equal to our original current linkage, which we'll call capital theta A. So we'll say that this is original coil, coil A, and coil B. And so we can write the Fourier series as this expression of phasors, like we've just been describing. And so we've got the expression for our original coil here, and now we'll create an expression for our new coil. And so the new coil is rotated by phi c from the first coil. And so we subtract, to express that, we take alpha minus phi c. Until we get this new series. And you can see that the Fourier series for the new coil, coil B, is the same as the Fourier series for the first coil, but each harmonic is rotated by e to the j n phi c. Each harmonic is rotated by the harmonic index times the coil's spatial rotation, n times phi c. And so we can now write an expression for our total current linkage in terms of just the fifth harmonic, and we'll talk about strictly the phasor of that. And we want this to equal 0. The only way this can equal 0 is if this term right here equates to pi radians. And so we observed that in order to make this happen, we need to have our angular separation be pi over 5, because each harmonic is separated by the fundamental separation times the harmonic index. So by doing this, that means the fifth harmonic between the new coil and the original coil are separated by 180 degrees, and since they're the same magnitude, you end up getting two phasors that are equal and opposite, and when you add them, you get 0. And so from this we can make kind of a fundamental observation that will come up a few times in this class, which is that if we shift a waveform by phi radians, all the harmonics shift by n times phi radians. So that concludes this video. In summary, we've reviewed the Fourier series. We've worked an example showing how to calculate the Fourier coefficients for a square wave, which happen to correspond to the current linkage of a full-pitched coil. We then talked about how to convert the Fourier series into phasor form so that we can talk about individual harmonics in our comfortable phasor notation. And we use this to study adding an additional coil to a winding to cancel out an individual harmonic. And as we get into winding design, we're going to be playing these kind of games where we look at the spacing between coils to fine-tune the harmonics of our current linkage or our back EMF.